For the second question of the exercise on rainfall losses, it was asked to perform a similar calculation as in the first question, but we will now not apply a constant base flow, but we will use a linearly increasing base flow. And to find this linearly increasing base flow, we will use the straight line separation method to find out the starting and ending point. We know from our theoretical lectures that the start of the storm runoff actually is the point where the river flow or discharge starts to increase when it starts raining. This will be quite easy to figure out where it will start. The end of the storm, however, is more difficult to find because this will be the location in time or the amount of flow where we see a change in the regime of river flow. And to find out this changing regime of river flow, we will use the logarithm of the river flow during the recession. And in this logarithm, if we plot that on a graph, we will see that we will be able to separate two straight lines. Two straight lines because they both correspond with one of the two regimes. First regime after the peak will be a regime where you have both base flow and storm runoff, and then afterwards in the second part, the second regime, you will only have base flow. The graphs would look a little bit like this. So the upper graph is the normal hydro graph, and you see that after the recession, after the peak here, you have a recession, and it's that part that we will plot on a logarithmic scale. The second graph here below, we have the logarithmic scale, and we see that we indeed have about two straight lines that we can separate. The point that we find here where they both cross is actually the point where our base flow will end. Here you see a value of, let's say, about 80. Should be something like that. And indeed, that's correct, because here, about 80 minutes after the time of peak, we see indeed that we have the end of the base flow, the end of the storm runoff, I'm sorry. Now for this method, the start of the storm runoff will be quite easy to find out. The start of the storm runoff in this case will be just the start of our discharge, because at the start we know that it's only base flow, and afterwards it starts increasing immediately. That's what we noticed already from our previous exercise. And then for the end of the storm runoff, we will apply this method. And you see from these two equations that we have indeed an exponential recession. The k value will be different for different regimes, and that's why if we put this on a logarithmic scale, we will get straight lines, and the k value will be the direction that we get. Now let's go back to our Excel sheet. We create a new sheet which we will call 2, and I will copy the values of the discharge and the time like this. Let's make this a little bit more nice, like that. So that's just what we have as data that was given for the exercise. Now I will calculate here the logarithmic value of the discharge, which I will not give a unit because that would not make sense. And here we can actually start calculating the logarithmic values of the discharge data, and we start it just from the recession on. This is the peak value, so we will start calculating the logarithmic values after that one. So let's say log, it can be natural logarithm or logarithm with a base number of 10, that's all the same. So we calculate it like this, and we end up here with these values. And that's now what we can plot. We can plot it, for example, from the start, here, like this. Let's go to graph, and we need a scatter plot. And then we see that we have our graph with points. Let's call this graph base flow. We can see immediately from this graph, let me add a axis title, especially here. This will be still the time in minutes, and also for the other one we can add a title which will be in this case logarithm of q, like this. But you can see from the graph immediately that we do have these two straight lines. Yeah, should be something like this and something like this. Now let's select additional points. So let's split this data set up into two. Let's add one, which we will call storm plus base flow, and it goes until the point 300. So let's select the numbers that we need from here till 300. So these are the time values, and the corresponding logarithmic values are selected for the y-axis. So that's our first data set. The second data set will be only base flow, because that's the second regime, and that starts from 330 on. 330 until the end. And also here, corresponding logarithmic values until the end. Like this. Now, to show the straight line, we add a trend line to these values. And we add the equation to this. Let's also make this a little bit longer, then we see where they cross. And also for this one, we add a trend line. We add the equation, and we add here, let's say 20. That's not enough. Let's add some more, let's say 50. Then we see where they cross. And they cross actually quite close to 300, the point here at 300. But we can also calculate that. Let's copy this equation, which is the representation of the straight line that corresponds with the regime of storm and base flow. Let's put it like this. And let's copy the other one. Like this. And then we can calculate the x value for which they actually cross. This x value is just obtained by putting these two together, and then we get a formula, an equation for the x value. In this case, this will be 0.0085. X is equal to 3.9572 minus 1.391. And to find the x value, we will actually say, well, this part here This will be equal to that divided by 0.0085. And this will be indeed a value close to 300, and this will be the value where they cross. To check this, we can calculate y based on both equations. So let's say minus 0.0095 multiplied with this value plus 3.9572. And we do the same with the second equation, minus 0.001 multiplied by this value plus 1.391. And these two are the same, so that actually means that we have the correct point where they cross. We could calculate based on this one what our flow value would be, because this is still the logarithmic value. So we say 10 to the power, this one, it would be 12.27. Now if we look at the values of the discharge, we see actually that we have around 300, we have 13.50. And it goes down a little bit, so 301 could be a little bit lower than 13.50. So we're very close to our point. To make things easier, we will actually use our point here at time 300 minutes and discharge 13.50 cubic meters per second. Just as an approximation, but that's already a very nice approximation. So actually this point will be the changing point between the two straight lines. So what we could do now is say, okay, we have our base flow in cubic meters per second. And that will start with our initial point, because at that time there was no storm runoff yet. And afterwards it starts increasing due to the fact that we have rainfall. So it will be 6, and we will use 13.5 over here as a second value. Now the values in between will be actually the values that are on this straight line between the 2 points, the linearly increasing base flow. Now to find out the intermediate values between 0 and 300 minutes of the base flow, we will calculate the equation for this straight line. And the equation would be, in this case, y minus 6 is equal to 13.5, let me put this into brackets, 13.5 minus 6 divided by 300 minus 0 multiplied with normally x minus 0. That would be our equation. Now let's transform that a little bit. That would mean that we actually get y is equal to 7.5 divided by 300, and it's 7.5x plus 6. That would be our equation. So if we apply this for the different values, if you would apply it, for example, for the first time step, 0, then indeed you see that y is equal to 6, because x is 0. If you apply it for 30 minutes, you would get, and let's fill this in, you will get 7.5 multiplied with the time divided by 300 plus 6, and that's 6.75. And now we can drag this up to here. So that's fairly simple base flow. And afterwards, actually, after this point where we have no longer storm runoff, the base flow will be actually equal to the total flow, because at that time there's no storm runoff anymore. So let's drag this up here as well. So that gives us the values of the base flow, and now we can actually perform the same calculation as in the previous exercise. So to make things easier, let's copy these two sheets like this. We make a copy out of this. Let's call this 2.1a and also graph 2.1a. We still have the same precipitation. Yeah, we have here the precipitation in cubic meters also. We have the same discharges, but we know that the base flow is different. So let's copy the base flow from this sheet into this one. And then we get indeed that we have a storm runoff up to the point where our base flow is equal to the total flow. And this gives us actually afterwards values of 0 of the storm runoff. So that's a correct representation. We could actually make a graph out of that one as well to show the difference. But I give that as an exercise for you to make such a graph. For the remaining of this exercise, we see that the storm runoff, of course we calculated this before, and we see that the storm runoff is now calculated again in cubic meters, so volumes. For that we use the same formula as before, so the value of the storm runoff in cubic meters per second multiplied with the number of seconds that we have for each time step. We do that for each of the time steps, and we get to the sum of all of these values. Similarly, we also did that for the precipitation, and we calculated the total volume of precipitation. Now, we also knew that to calculate the net rainfall based on the constant runoff coefficient model or the proportional loss model, we need to calculate our runoff coefficient based on the total volume of storm runoff divided by the total volume of precipitation. And we still had this calculation over here, because here we use the total volume of storm runoff and divide it by the total amount of precipitation. And this gives us a runoff coefficient of 0.238. If we compare that to the runoff coefficient that we found in the first question, we see that it's lower, and that's logical because in the first one we had more base flow. There our base flow was constant until the end, and here we have a base flow that actually linearly increases and then afterwards is equal to the total flow. So our storm runoff that we see in here is much smaller at certain time steps, actually at every time step, compared to our first question. The runoff coefficient is then used to calculate the net rainfall, and let's do this now in a proper way. Subscript, okay. So the net rainfall is calculated based on the total rainfall intensity, so the effective rainfall intensity, multiplied with our runoff coefficient. And this is done for every time step. And the losses are calculated by subtracting the net rainfall from the actual rainfall. Again, we could make a graph out of that one, and that should be automatically adapted in this case because we copied it from last time. And if we compare this graph with the graph in 1.1a, we will see that indeed due to the fact that our runoff coefficient is smaller, which means that there are more losses actually, we see that indeed our net rainfall is smaller than in the first question. It's only a slight difference, but you can see the difference. Similarly, for our second part of the question, so for B part, we can copy this graph, these two sheets, and put them at the end. .1 B and 2.1 B, like that. And we can replace the base flow that was constant here by the base flow that we found by applying the straight line separation method. So we paste this and we get indeed again our storm runoff, which is much smaller. Now here we have to take care that we do this in the correct way. Of course, our highest peak of precipitation, let's recall this again, what we needed to do for the constant loss rate model or the phi index model. There we said that we start by assuming that only the highest peak contributes to the storm runoff or to the net rainfall. We calculate the phi value based on that assumption, and if the phi value is smaller than the second highest peak, we knew that the assumption was wrong. And we go on like that with 2 peaks, 3 peaks, 4 peaks if necessary, and each time we check if our assumption was correct. For the calculations, we use the formula that is mentioned over here. So to calculate phi, we actually sum up the pulses or the peaks of rainfall that would, in our assumption, contribute to the net rainfall, to the storm runoff, and then we subtract the actual net rainfall, the total net rainfall from it, and divide it by the number of peaks involved. So if we have the assumption that 2 peaks are involved, then we divide by 2. This is unknown at the start because that's what we are searching for, but it is equal to the total amount of storm runoff. So let's get back to our Excel sheet. We have the correct base flow, we have the correct storm runoff, and we have our precipitation here. So for the first step, it's crossed already. Let's make a normal out of this to check it. We say, okay, we take the highest peak, yeah, and we subtract the sum of all of these. And we're working in both cases in millimeters per hour. Now, what the value that we get is 86.74. And just like in the previous question, we see that there are 2 peaks that are actually higher than this 86.74. And that means that we don't have a correct assumption. We have more than 1 peak that is contributing. So we can adapt this again. We can cross this because this is wrong. But maybe the second one is now correct. Let's check that. Let's assume that our 2 highest peaks, 136.4 and 105.6, are contributing. So we sum those up and we subtract the sum of all storm runoff, both expressed in millimeters per hour. And we divide this by 2 to take into account that we have 2 peaks. The value that we get is 96.17, and it's only slightly, but it is smaller than the third highest peak of 96.8, which actually means that this peak would also contribute to our storm runoff and to our net rainfall. So that's also a wrong assumption. We have not 2, but in this case 3. So this should be crossed as well because it's wrong. We apply again the third assumption, 3 peaks contributing to the net rainfall. We sum them up, we subtract the storm runoff, and we divide by the number of peaks involved, namely 3. And then we get a value of 96.38, and that is actually larger than any other remaining peak of rainfall, any remaining pulse of rainfall. So in that way, we know that our phi value will be 96.38 millimeters per hour. We can fill this in, which was done automatically in this case because it was already programmed from the last question. And we can calculate our net rainfall based on this. As long as the phi value is larger than the actual rainfall, we get a net rainfall of 0. When the actual or effective rainfall is higher than the phi value, we subtract this phi value from our actual rainfall. And so we get our net rainfall for this storm. The losses are just the difference between the actual rainfall and the net rainfall. So in the cases where there is no net rainfall, this will be the total amount of actual rainfall. And then for the cases where there is some net rainfall, this will be equal to phi. If we put this into a graph, we see a similar image as in the previous question, so in question 1. And there we see actually that again the storm runoff was smaller, so the net rainfall will be smaller as well. So it's only slightly different, but there is some difference between question 1 and question 2. So that brings us to the end of the first and the second question. So we calculated now not only the net rainfall based on the constant base flow, but also based on a linearly increasing base flow. And we applied the 2 methods, so both the runoff coefficient method and the phi index method, to calculate the net rainfall. If you want to try to do this calculation again, I invite you to do that. It might be a good exercise to do this twice instead of copying it from our first try.